Guys, where is the rest of everything? Bringing everything up. How are you guys today? Hopefully you guys will get here pretty soon. Hope you guys are having a good week. It's been nice and sunny out. Monday was kind of gross, but the rest of the week's been really nice. Good, just going. I've been going to a virtual conference all day, but it ended early, so we could have class. Super. Are you guys? It's going. Things are coming along. Yeah, I think this material really starts to put the material from chapter 2, 3, and 4 really all together in maybe, I don't want to call it a more interesting way, but in a different way, which is, in my opinion, super nice. So, anyone have any questions while people are popping in? You can go ahead and drop it in the chat box. I have not finished grading your mini exams yet, but I am hopeful that they will be done by Friday. So I have started. When they are done, I will release all of them at once. They will be done no later than Monday. Sorry, I forgot to include the videos for the week. Just totally forgot until a couple of you guys had emailed about it, and so I was like, oh. Any other questions? You have Alex due on Monday. Your Alex scores for the completion scores for the last 2 weeks will go up sometime this week, maybe today, for sure by Friday. Those are basically just what percentage of your objectives you get turned in every time. Your next open pie is going to be in 2 weeks when exam 2 is. So exam 2 is in 2 weeks, and then we'll go there. Yeah, there's a lot of different places where you can find information, but I like it when people send me just an email reminder most of the time. So if you ever forget or get lost, you can, as Mary says, it is on the modules page. Jenna asks, random question. It's exciting. Why does Alex give us such a weird explanation on how to do the problems? So Alex is modeled out of an engineering math background, and sometimes they tend to think about the processes in a different manner. You can do them the method that I teach or the method that Alex does. For the most part, you should always get to the same place. Sometimes Alex kind of goes through some really odd mechanisms to get there. My suggestion would be to watch my videos, come to this, then to your Alex, so that if Alex is giving weird explanations, that you can kind of ignore those. I know that happens often, but in very random places. So that's just why Alex. Yeah, I would, if the explanations don't help you, don't read them. You can reach out to me. I can try to help you in other cases. So Christopher asked, what materials on the next exam? It will cover chapters 4, 5, and 6. So we're almost halfway done. Maybe we're a little, by the end of the week, we will be most of the way through the material. Unlike exam 1, we're kind of all built up together. Exam 2 has basically 3 different buckets. Chapter 4 bucket, chapter 5 bucket, and chapter 6 bucket. Some of those will intermingle well together, and some, like a lot of what we're going to do today, won't. Let's see if I missed any other questions. Any other questions today? Or we can start working problems. There are 10 of them. I think I might have gone a little overboard. We will do our best to figure that out. So you should be able to answer Alex using more than one method. So Alex ALEKS will force you to do it over and over again. It doesn't tend to ask for stepwise calculations. In the cases where it does, it's asking you to basically reconfigure some of the questions that I've asked, particularly the fill out the table things. I know that students find those particularly frustrating. So, but I think we will start with question number 1. I think as soon as I move out of the way, y'all can read it. Okay, so our first question today is, what is the enthalpy change of 69.1 grams of aluminum hydroxide if 69.1 grams of aluminum hydroxide decomposes in the following reaction? C reaction. So what this gives you, and I think in chapter 5, it becomes really imperative that you start reading the whole question. So there have been a lot of things I've asked you to learn or memorize. In this case, you have to be provided either a way to calculate delta H reaction or delta H for a reaction. So in this case, it gives us that information. Sorry. So because it gives us a reaction, we know that delta H reaction generates negative 41.2 kilojoules of energy, 100% of the time. So it's asking about the aluminum hydroxide, which is right here. And so there's two things at play here. We need to figure out how much aluminum hydroxide we have and how it relates to what's in the problem. So the first thing we're going to do is convert to moles. So we're going to take 69.1 grams of aluminum hydroxide. We're going to convert that into moles using the molecular weight of 77.85 grams in 1 mole. And that equals 0.8876 moles. So once we can determine the amount of moles of aluminum hydroxide, now we can start to think about what the problem tells us. So we're going to take our our negative 41.2 kilojoules from the equation is per any component in the equation. So that means it's per 3 moles of water, or 1 mole of aluminum oxide, or per 2 moles of aluminum hydroxide. So this is the kilojoules per mole. Now, a lot of times students just want to drop a line and write mole underneath, but that comes from this. So if it is a defined kilojoules per mole of aluminum hydroxide, then it would be different. Now we're going to multiply that by the number of moles that we have, 0.8876 moles. And so from here, we can cancel out our moles and determine our kilojoules. So if we plug this in our calculator, we get 18.28 kilojoules. And based on sig figs, we get 18.3 kilojoules. So it's actually not negative, but my paper does not have the questions on it, and so I thought the equal sign was a negative sign. That's why it has a negative sign on it. So in fact, it's just 41.2. Thanks for catching that. So in this case, so if you missed what was happening, I had said that this was negative because I don't have my glasses on, And the equal sign looked like a negative sign because the font's not that big. So while you think about what questions you have, let's go ahead and work on part B, because it's the same type of question. It says, what is the enthalpy change if 78.1 grams of water is produced in the reaction shown? So now, instead of thinking about the aluminum hydroxide, we're just going to use water. So we can take our 78.1 grams of water, and we're going to convert that into moles using the 18.02 grams of 1 mole of H2O. Now we also know that it's 41.2 kilojoules. But in this case, it's per 3 moles of water. And this number comes directly out of the balanced chemical equation. So when we plug this into our calculator, we get 59.5 kilojoules. So what questions do you guys have about this type of question? The ability to convert the enthalpy from reactants or products to give this information. Later this class, this week, we are going to learn how to calculate delta H. For this problem, you were provided delta H. If you don't have any questions, you can go ahead and drop none in the chat or really anything, just like a letter, a number, an emoji. I'm going to go ahead and get out of the way so you could actually see the work. But I have to walk back to the other side. Thanks, Zach. While you guys are processing that, I will go ahead and put up the second question. Let me see if I can make that font bigger. Emma. So Emma's question now needs the other one back up. So hold on. So in this case, the delta H reaction right here, this value, tells you for this exact scenario how much energy you get. So we're asking if you have less than that. You can think about it. So sometimes when you get a pint of ice cream, it tells you how many calories it is per serving, or it tells you per, like, the whole thing, right? So in this case, you can think of this as the calories per container. And then we want to ask ourselves, well, maybe we didn't have 3 full moles of water. We only had 1 mole or 2 moles. So then this value here is per any quantity found in the balanced chemical equation. So Dean asked, how do we go from 1 mole to 3 mole? This calculation here is the grams to moles calculation. This is to determine the delta H per the amount that you had. So in this case, what you want to do, and we'll see some different ways to look at this, Dean, whose question I'm attempting to answer, so it's this per the amount in the problem, and we want to set that up to account for how much we started with. Y'all are having great questions today. Make that go away. our next question is to calculate the energy required to heat 0.5 kilograms of silver from negative 3.2 Celsius to 15.6 Celsius. Assume the specific heat capacity of silver under these conditions is 0.235 joules per gram Kelvin. So in this case, we're going to use the Q equals MC sub s delta T. Now, in chapter 5, a lot of the different topics are really all going to use the same words. So the real question is, which equation do you want to use? So sometimes you'll read the question and be like, I know. But if on the exam or in Alex, you get to a point you're like, I'm not really sure what to do. My best suggestion is to write down everything the problem tells you and then frankly go looking for an equation that asks for that. So in this case, we have, it tells us C sub s is equal to 0.235 joules per gram Kelvin, okay? So then it gave us a mass of 0.500 kilograms. Well, we want to use this unit. So we need to convert that to grams. So that's going to be 500 grams. So we have 2 out of the 3 values in this equation. So then it gives us 2 temperatures. So delta T is T final minus T initial. So our final is 15.6 minus a negative 3.2. And that gives us 18.8 Celsius, which is equal to 18.8 Kelvin. Now, that's only because it's delta T. Because Celsius and Kelvin both use a 1, like the 1 degree Celsius is the same as 1 degree Kelvin, like the increment between the two. So we can use delta T directly calculated from Celsius. You can't always do this. I will tell you when you can't. But for the most times in chapter 5, you can use Celsius as is. So from here, we can plug this into our calculation where we have M, which is 500 grams. C sub s is 0.235 joules per gram Kelvin. I ran out of space. So then we're going to put our 18.8 Kelvin. So a lot of times we don't, that's never going to work. Let me erase this and move it over. So we have 500 grams times 0.235 joules per gram Kelvin times 18.8 Kelvin. So one of the biggest issues where students get kind of messed up is they don't remember to cancel their units. So if it asks for it in kilojoules, you want to make sure that it's asking for that. Or you might have caught that you had a 0.5 kilograms when you try to cancel grams and kilograms. So when you plug this into your calculator, you get 2,209 joules. And so we need to only have 2 sig figs. So in this case, we're going to get 2,200 joules. I do not care about scientific notation. Alex will obviously ask you to make that 2.2 times 10 to the third if this were to come out of there. So what questions do you guys have that you can't see because I'm standing in the way about this question and using the Q equals M C sub s delta T? If you have none, you can go ahead and drop that in the comments. these calculations, the bigger issues, in this one it's quite easy. Some of the others are a little bit more complicated, but basically the same. Nice. So both Christopher and Dean are asking, why did it round? So in this case, because you could only have two significant figures, because of both the 500 kilograms and the 3.2, well, this only had two, so our answer can only have two sig figs. And so because this is the place that counts, it's a 0, so it rounds down. Good question, though. So in this question, we have a coffee cup calorimeter, and when 1.38 grams of liquid PCl3 at 25.55 degrees Celsius is added to 342 grams of water, also at 25.55 in a coffee cup, the temperature of the solution increases to 32 degrees. If the specific heat capacity of the solution is 4.184 joules per gram Kelvin, calculate the heat released in this reaction. So in this question, we are also going to use the same equation of Q equals M C sub S delta T. Because this is asking about the heat released, we are going to also, we're looking for heat of the reaction, which is negative M C sub S of water delta T of water. Now, if you are quite curious as to why there is a negative in this sign, that probably means that you didn't watch the calorimetry video. I'm going to suggest that you watch that. Obviously not right now because this is our live hangout time, but that will clarify why sometimes I use a negative equation and sometimes I don't. So from here, we're going to look for our three values. And so we're going to start with C sub S. And that's 4.184 joules per gram Kelvin. Delta T, in this case, is T final minus T initial. And so we're going to go from 32.00 to, or we started at 25.55, and that gives us a value of 6.45 Kelvin. In this case, the mass, and here's the hard part, is the total. Because the mass is everything in the system, both the water and the other component. So we're going to take our 1.38 plus 342, and that gives us 343.38 grams. Now, my recommendation, I know this value per sig fig should actually pair back to 343. My recommendation is to carry it forward and trim at the end because there's some of the other values that will control our number of sig figs a little bit easier. So now we're going to calculate Q reaction. And that's negative the mass of 343.38 Q reaction equals negative 343.38 grams, 4.184 joules per gram Kelvin, times 6.45 Kelvin. So from here, our units, our Kelvins cancel, our grams cancel, and that's going to, when we plug this into our calculator, give us negative 9,266 joules for this calculation. Now, from here, it asks us how much heat is released. So in that case, it's asking for the absolute value of the heat. In this case, so that makes it, absolute value means it's going to be positive, and we can only have 3 sig figs. So in this case, Q equals 9,270 joules. Questions today? Did we feel like this was easy? Did we feel like it was simple? What are our thoughts about this equation? So Zach asks, why is it the absolute value? Because it asks for the heat released as opposed to what is the heat at the end of the solution. If it asks you to calculate the delta H of reaction for this process. So because it asks for the heat released, you can't release negative heat. It tells you that in this case there is heat released. So it's asking for the heat released, so it's a positive number. If it asks you for what is the heat change, then it is a negative number. Does that make sense? Feels like kind of. All right. If we can't make that a little bit easier for y'all to see. Nice. So the next 2 questions that we had are on Hess's law. Hess's law is, in my opinion, best tackled as if it was a Rubik's Cube or a Sudoku puzzle, or really any type of we need to manipulate the parts in order to see the whole. So the way Hess's law works is that we are asked to calculate something using other information. So what we want in this case is to make sure that what we're seeing is the answers. So this one, we are looking for the change in enthalpy for the following reaction. This is what we're looking for. And we're going to use this equation and this equation. On a mini exam, we don't have one of those for the exam. But for the exam, you may have to rewrite them. You can also annotate them as do this to equation 1, do this to the equation 2. And I will try to include that in the exam where they'll be noted like equation A and B. So we have 2 equations. Let me make sure I'm below the writing. So we have CH2CO. I'm going to eliminate all of the states just for the ease of writing. Plus 2O2 goes to 2CO2 plus H2O. And our other equation is CH4 plus 2O2 gives us CO2 plus 2H2O. So we have an equation. The parts, we're going to add them up together in order to get that. So what we're going to do is we're going to look at this, and we're going to compare it to the equation we want. Now, you'll notice we have oxygen in both, okay? We have water in both. But we have methane gas and CH2CO. Those are not on the same side. So we need to be able to flip the equation around the arrow in order to figure that out. So we're going to flip this equation. And so that will give us CO2 plus H2O gives us CH2CO plus 2O2. And when we flip it, the delta H is going to become positive 981.1. Do this. There you go. So we flipped our first equation, and now the delta H, which was negative, and you can find that, I think, right up here in the problem. So for the second equation, we're going to look at what our product is. And so right here, it tells us that we need to have 2 methanes. Well, in the equation, we only have 1. So we're going to multiply it by 2. Multiply by 2, so now we have 2CH4 plus 4H2O. Nope, 4O2, sorry, gives 2CO2 plus 4H2O. So in this case, now we're going to start to cancel out anything we see on both sides. Because we want to total them up. If I could raise the board, I would rewrite it, but it turns out I can't. So what we see on both sides is we have 2 CO2s. So those are both going to cancel out. And we have 4 O2s and 2 O2s. So this is going to cancel out. This will go to 2. We have 1 H2O and 4 on the other side. And so when we rewrite this equation, we're going to end up with 2CH4 plus 2O2 goes to CH2CO plus 3H2O. This is what the problem asked for. So our delta H is the summation of the 2 values of positive 981.1 plus 2 times negative 802.3. So delta H of this reaction is negative 623.5 kilojoules. Now, a really popular question is, well, what are we going to have to come up with? Nothing. A question like this, all of this information up here, perhaps organized in a different way, would show up for you. It would say, determine delta H of this reaction using these reactions. And those questions would also come with the delta H reaction values. So what questions do you have about this example? Oh, right. I'm still in the way, y'all can't see. If you don't have any questions, feel free to drop a none in the chat box. That way I know that you're ready for the next Hess's Law example. So Hope asks, when you multiply everything in the equation, right? That is definitely correct. So when you multiply by 2, every single chemical gets multiplied by 2, as well as the delta H gets multiplied by 2. Christopher asked, did you subtract the delta H's? No, you add them. One is positive and one is negative, which gives you an overall negative value. Unless you're asking a different question, Christopher, I assume you're asking where did this number come from? It's positive 981 plus 2 times the negative 802. There we go. Sorry. There we go. So in our next example, I think this one is formatted better, in my personal opinion. I wrote this one, the other one I collected from other places. So Dean has a question, so we're going to go ahead and put that back up there. That was an equal sign here, but this is just the value 2, Christopher. So Dean asks, where did Dean's question? Why did we flip it and multiply? It's a really good question. So in Hess's law, we want to use the equations we have. These are our knowns. And we want to create this equation. So we're going to modify these. So this is a product in the equation that we have. And so we want to make sure it ends up on the product side. So it turns out that chemical reactions are a little different than everything else in life. You can put energy in to go this way. And if you wanted to go this way and you just reversed, you get the same amount of energy out. So you can flip it and then change the direction and the sign, because it means it takes, I don't know, we'll say 10 kilojoules to go this way. But then to go that way, if you put 10 kilojoules out, to go backwards, it would give off 10 kilojoules. Normally, for us, it costs energy in both directions. So it's a little bit of a weird concept. But we multiply by 2 because it turns out that we can in order to make this into anything else. See if there's any other questions. Dammy, I think Mahi has answered your question in the chat about how this negative value flips signs when you go in the opposite direction. Great questions, you guys. So let's look at another example, because I find, in my experience, Hess's law is best learned, frankly, by looking at it multiple times. Some of the other calculations are the same, like grams to moles is always the same calculation. However, in this case, the more examples you do of this, the better it is. The other thing I'll tell you is these examples, you can either find them in the book, you can redo the questions in the PowerPoint slides, or you can do the chapter worksheet. There aren't any in Alex. We all know that Alex likes to do stuff a little bit different. It turns out that their Hess's laws, they're like a lot different. And the way that I'm teaching you guys how to do it, what they're asking you to do is not the same. So it is not going to be in Alex. It will be on exam 2. So in our next question, we are looking for the delta H of reaction of 4 ammonia plus 5 O2 to create 4 nitrous oxide plus 6 water from the following data. So we have these equations, which we have an equation and a delta H. I will always give you all of this in order to do that. So we're going to look at each equation individually. If you try to turn all of these together, it is possible. But I find when you look at the first equation and ask, where does this thing need to go in this equation, and then see what happens, sometimes that's a little easier. So the first thing we're going to do is for equation 1, I'm going to multiply by 2 to where we get 2N2 plus 2O2 goes to 4NO. And so our delta H is going to equal negative 2, nope, it's 2 times negative 180.5. So now the next equation. So this is N2 plus 3H2 gives us 2NH3. If we look at the equation at the top, we need the ammonia as a reactant. So we're going to have to flip equation 2. But we need 2 moles of ammonia. Nope, we have 2 and we need 4. So we're going to flip it and multiply by 2. Whoops. Flip and multiply by 2. So this is equation 1, this is equation 2. So when we flip it, we're going to get 4NH3 goes to 2N2 plus 6H2. And delta H in this case is going to be 2 times positive 91.8. Make sure that's still in frame. So again, in this equation right here, it is negative. But because we flipped it, it's going to be positive. So for our last one, we have 2H2 plus O2 gives us 2H2O. And in the equation up here at the top, we need 6 moles of water. So we're going to take this one, and we're just going to multiply by 3 to where we have 6H2 plus 3O2 gives us 6H2O. And so our delta H is going to be 3 times negative 483.6. So now, in order to see if this works, we need to total everything up. You'll notice I tried to line up my arrows. The reason I like to do that is because it makes it really easy to ask, is something on both sides? If you don't, it's kind of like trying to play match with things that aren't lined up. Notice that the N2s, there's 2 moles of each on both sides. Those are going to cancel. We have 6 moles of H2 on both sides. We're going to get rid of that. And it looks like we have nothing else that cancels. So our equation will be 4 moles of ammonia plus 5 moles of O2. The 5 came from the adding the 3 and the 2. And that gave us 4 moles of NO plus 6 moles of H2O. And so our delta H is going to be the adding of these values, which gives us negative 1,628.2 kilojoules. So what questions do we have? Do we feel a little bit better about Hess's law after this example? Sorry, I know. You'd think by now in the year I'd know how to be out of frame. So in this case, the hardest part is trying to figure out what do we do with each equation? And what do we do with the information that we have? So I always write out what I've done so that you can look at it. Sometimes you will notice in some of the examples, you'll be given 3 equations and you only need 2. That happens sometimes. So what questions do you guys have? And if you have none, as always, you can just drop that right in the chat box. Hesse's law and the stuff we're going to do next, I just really like it. I find it makes it very clear. It's easy to find the answer. So Dammy asks, when we cancel out, does it matter what order it's in? No. You could have written these in a different order because we know that a reaction, the reactants, the order of those doesn't matter. It does matter if they're on the left side of the equation or the right, but you can write them in any order. I tried to match what we were asked for just for clarity, but you don't need to. You should, however, always verify that this matches what's in the problem, because every now and again you'll flip something that shouldn't have been flipped, and when you sum them up, that will become pretty clear. Good question. Other questions? Bunch of weird noises in the building today. Oh, that's a little weird. Let's make that actually bigger. So our next question, we're going to move to a new topic. Now we're going to start to calculate delta H using heats of formation. A heat of formation is how much energy it takes in order to make something. So in a question that you guys can't read because it's covered up by the board, it tells us, given the following standard of copper oxide plus hydrogen gas goes to copper solid plus liquid water. If we know that the delta H reaction is new plan, we're actually going to do number 7 first because it will be easier to talk about number 6 afterwards. So let's try this again. We will come back to number 6 after, probably we'll do 7, 8, and then we'll go back to 6. Just so we know. So in this case, we are given a table, which you can see right here. On the exam, you will also have a table. It's important to note a couple of things about this table. One, this state of matter. Sometimes you'll be provided lots of different options in this table, and you'll need to select which ones you need. So we're being asked to calculate delta H reaction for the SO3 gas plus H2O liquid to create H2SO4. So we're making sulfuric acid. So in order to calculate delta H using the delta H not F table, we need to remember that delta H reaction is equal to the sum of the delta H not F for the products minus the sum of delta H not F for the reactants. So this information comes directly out of the table. So in this case, we will calculate that delta H reaction equals delta H not F of H2SO4 minus delta H of SO3 plus delta H of H2O liquid. Now we can plug these values in from the table. So it's negative 814 kilojoules minus negative 396 plus negative 286. And when we plug this in our calculator, if you've used your parentheses correctly, you should get negative 132 kilojoules. I don't like this table being over my face at all. Let's make that a little smaller. Perfect. So, one, you will always get this table. I will provide it for you. Some of the worksheets tell you to open Appendix C in your textbook. You can also Google delta H naught F tables, or you can complete it using the heat set formation tables that are provided in ALEKS. The biggest tricky spots are over here. If you don't use parentheses for the anything where there's more than one, it's possible that the signs will become a little not right. So you need to make sure that it is the sum of the products and the sum of the reactants. You can set that up in your calculator using parentheses. So what questions do we have about number 7? We have another one very similar to this here in just a second. All right. Do we think this was easy? Do we think it was hard? Do we... So again, we've got ourselves a little table. And so we're basically, in this case, going to calculate the delta H of reaction for silver sulfide plus oxygen going to silver oxide plus sulfur. So in this case, we're going to do the exact same thing. So I'm going to leave up our equation because that makes life easy. So the first thing we want to do, the first thing I always do is write down all of the things we need. And I do that so that for 2 reasons. 1, you are more likely to get partial credit the more stuff you write down. And 2, it makes it easier to go looking in this table for what you need. So the delta H naught F of the products, in this case, will be 2 times delta H of Ag2O plus 2 times delta H naught F of sulfur. And that's going to be subtracted from 2 times delta H naught F of Ag2S plus delta H of O2. Now, you might have looked at this table and noted that some of the values you need are not present. I gave you 4 values, but not all of them appear in this equation. So the thing that you want to remember is that anything in its native state or by itself, oxygen gas, sulfur, actually has a delta H naught F of 0. So in that case, this is going to become 0, and this is going to become 0. Think about it this way. It's asking how much energy does it take to make something. If you can find it the way it is in nature, you don't have to make it. But if you needed liquid oxygen, that in fact does have a heat of formation, but oxygen gas doesn't. I will not ask you about things that are very odd, but I will ask you about diatomics or elements in the periodic table. So if it's an element by itself, more than likely it doesn't have a heat of formation. So now we can plug these values in. So we have 2 times negative 31.0 plus 0 minus 2 times negative 32.6 plus 0. So the delta H of reaction in this case is 3.2 kilojoules. What questions do you guys have, once I move out of the way, for this calculation? Did you guys find that it was easy? So now let's do something a little different. We'll bring back number 6. So in this case, hold up. Sarah asks a question. What is some of the values of the equation used delta H not? Sorry, Sarah, your knots got me a little confused. So why do some of the values in the equation not use delta H not F? Probably because I didn't write it down. All of these are delta H not F values, and they come out of this table. Hope there is lots of practice. This will be in Alex, but I don't think they go crazy on this topic. But I've thought that before and been proved wrong. Dean asks, how do we get a 0 on the 2? Great question. So anything in its native state, in its normal state, such as oxygen gas, that's how we find it if you were to go to the element store and buy oxygen. That, because it doesn't have to be made, has a delta H naught F of 0. In this case, for sulfur, it also has a delta H naught F of 0. Although sulfur 8 is also the natural state, sulfur is a little weird, but in this case, it does equal 0. Okay, so next, let's look at this example. So now, instead of being asked to calculate delta H reaction, we're being asked to calculate delta H naught F of an element in an equation. So similar topic, but a little different, which is why I like doing this one after the other two. Because we've looked at this and determined how to solve for these. But what we also want to be able to do is calculate what this is instead of just calculating delta H reaction. So in this case, we also have the delta H reaction is equal to delta H naught F of copper plus delta H naught F of H2O liquid minus delta H naught F of CuO plus delta H not F of H2. Ooh, let me move you over. Give you all a little bit better view. There we go. So we have all of this information. In this case, we're being asked to solve for this. This is our unknown. So we need to figure out everything else that we do know. So it turns out that copper in its elemental state is also equal to 0. Okay, good news. As is hydrogen gas. And we know delta H naught F, and it is right here in a kind of terribly, poorly laid out shenanigan. But we also know delta H reaction because it is right here. So we know that we have negative 129.7 kilojoules, and that equals delta H naught F of water, which is negative 286 kilojoules, minus delta H naught F of copper oxide. So it's asking us to solve for delta H naught F of copper oxide. In this case, when we do that, so when we subtract the negative 286 from both sides, we get 156.3 kilojoules equals negative delta H naught F of copper oxide. Therefore, delta H naught F of copper oxide is equal to negative 156.3. Now, you're probably asking yourself, wait, what happened here? Bring you a little bit closer. Come into my classroom. Okay, so here's what happened. This is the math thing. We have negative 129, and we have negative 286. In order to move this on the other side, we're going to add 286. That negative sign is quite light. So when we do that, we're going to get positive 156.3. But wait. We have a negative sign here because it is this minus that. Now, when we do that, we have to keep track of that negative sign. So the negative delta H naught F really just comes from the fact right here that it was a subtraction. So then in order to solve for delta H naught F, we're just going to put the negative sign on the other side as seen on the other side of the equation as seen here. So I say all of this to remind us that these minus signs can be negative signs, and so we want to make sure that we're keeping track of them, particularly in these types of cases. So what questions do we have about this example? If you have no questions, you can go ahead and drop that right in the chat box so that I know that you are ready to move on to our last two questions. Did we think this was easy? If you don't have any questions, you could drop an emoji. You could drop the number 3. It's a little different. Well, Zach, you're right. I forgot that there was a part B on this question, so we'll do that right over there in just a second. Thanks for catching that. Hope, I agree. This one has a few little tricks and twists along the way. So, as Zach mentions, it turns out that we have more to this question. So, I'm going to solve that part of the question right over here. So, the second part is, what is the enthalpy change if 3.203 grams of copper is created? So, in this case, we have a delta H reaction. So, this is very similar to what we learned at the beginning of Chapter 5 with an enthalpy change. So in this case, we have our 3.203 grams of copper. And then the grams per mole of copper is there are 63.55, that's not big enough, grams of copper. And due to space, we're going to 3.203 divided by 63.55, which gives us 0.0504 moles of copper. And then we're going to multiply by our delta H reaction, which is negative 129.7 kilojoules. And that, in this case, per the equation, is per 1 mole of copper. So we're going to multiply that by negative 129.7. What you mean? We're going to get negative 6.5234 kilojoules. Nice catch. Any other questions about this? Otherwise, we are going to move to the very beginning of chapter 6, which was one of the videos for the week. So, let's make that a larger font so that you can see it. So, our next question has to do with light. So chapter 6 is going to pick back up electrons. We left them at the end of chapter 2. Like we said, hey, there's an electron. Now we're going to talk about where they are. So if you took high school chemistry or intro to chem or have watched all the videos for this semester, you'll know that electrons live in orbitals, places such as the 2p orbital or the 5d orbital. We are now going to learn how those came to be and where they are. But before we do that, we're going to talk a little bit about light. So light is basically how fast, which is the speed, or the frequency of light, which is related to the wavelength. So in this case, we are asked for the frequency of light in kilohertz of a laser pointer that emits light at 723 nanometers. So the speed of light is equal to lambda, which is the wavelength, times the frequency. So in this case, they gave us the wavelength, so we have the frequency equals lambda the speed of light divided by the wavelength. So we have 2.998 times 10 to the 8th meters per second. divided by the wavelength of light, which is 723 nanometers. You'll notice that nanometers and meters are in fact not the same unit, so we need to convert. So there are 1 times 10 to the 9th nanometers in 1 meter. Or you can flip that. You can set this up in a variety of different ways. And so when you plug this into your calculator, you get that the frequency is equal to 4.146 times 10 to the 14th in 1 second, or in seconds to the -1, so let's write that, which is the same as hertz. So the question asks for you to calculate that in kilohertz. And so there are 1,000 hertz in 1 kilohertz. And so that gives you 4.15 for sig figs times 10 to the 11 kilohertz. So in light, in this section of light, we really are going to start to manipulate equations again. As I talk about in the video, I often manipulate my equations without numbers because it's a little easier for me to see. What questions do you guys have? And if you've got to go, you can go ahead. I will stay and solve this. There's one more question. Otherwise, if you need to go, you can. I will stay and solve the next one. Any questions? I feel like today we're all kind of rowing a slow struggle. We'll go ahead and put up number 10. Give you guys another couple of seconds for questions. Then we will solve the energy of a photon of light at 562 nanometers. Nice, I'm glad you think this is pretty easy. This is a relatively traditional plug and chug. I will remind you that the speed of light, and in the next question we're going to use Planck's constant. Those will be found on your equation sheet, which in the Canvas quiz is like at the bottom. But feel free to write them in your notes for your study guide. So our next question is going to use the fact that photons have energy. And so in this case, the speed of light we know is c equals lambda nu. And the energy of a photon, E photon, is Planck's constant times the frequency. So we can do either some equation manipulation, or we can use the speed of light to calculate its frequency and then plug it in here. I'm going to choose to manipulate my equations. To create an equation for this, where the frequency is equal to c divided by lambda, and then I'm going to plug that into this equation, to where the energy of the photon is equal to Planck's constant multiplied by the speed of light divided by the wavelength. Now, all I did was take this equation, manipulate it, and insert it in this equation in order to determine the energy of the photon. So Planck's constant is 6.626 times 10 to the negative 34th joule seconds. multiplied by the speed of light, which is 2.998 times 10 to the 8th meters per second, divided by 562 nanometers. Now, again, nanometers and meters are not the same. So there are 1 times 10 to the 9th nanometers and 1 meter. And so when we plug this into our calculator, we're going to get the energy of the photon is 3.5, how many sig figs do we have? 3.53 times 10 to the negative 19 joules. What questions do we have? Did we also find this a relatively easy calculation that I'm now standing in front of? Any other questions today? I know that we moved a little bit fast and looked at several different topics today, but all of these are the topics that we'll need in order to move forward this semester. If you don't have any questions, feel free to say bye in the chat box, and I will see you guys next week. Or feel free to come to office hours. They are back to normal starting on Monday, and I am more than happy to meet with any of you if you just send me an appointment email. Emails are a little slow this week just because I'm attending a conference, but otherwise I'm looking forward to seeing what you guys have. Bye, Hope. Bye, Zach. Have a great afternoon. Bye, Ashana. Bye, Daquan. Y'all have a great rest of your day. It's good to see you virtually. Bye, Anissa. Y'all have a great week, too. Enjoy the nice weather. Y'all have a great rest of your day.